the coding technique at each end. The additional sources of delay could be a delay caused by equipment and, in theory, propagation delay. Propagation, of course, means traveling from one place to another. And when we're discussing communications today, we're talking about energy traveling using fiber and optics. And the speed of light inside glass is about 2/3 the speed of light in a vacuum. So we start thinking, well, what is the speed of light? And how far are we talking about going? Well, just as an example, let's say we're going across North America, and it's a lot easier to use metric to do these calculations. Let's say we're going 5,000 kilometers. The speed of light is 3 × 10⁸ meters per second. So if we divide 5,000 meters by 3 × 10⁸, we end up with a delay of around 20 milliseconds. And then, since light travels more slowly in glass than it does in a vacuum, maybe we end up with 30 milliseconds propagation delay going from one side of North America to another. So it's not insignificant. If you're going up to a satellite, that would be well over 1,000 milliseconds. So it's unclear that you could do voice over IP over a satellite without having lots of trouble with echoes that you would have to figure out that the manufacturer of a product that had been designed for fiber optic based systems had not taken into account. So you've got to be a bit careful about that. If we're talking about going from one side of the planet to the other, then the fiber optic based delay could maybe go up to 60 or 70 milliseconds, and so it might start becoming significant. Now, besides propagation delay and delay caused by the compression functions, then the other one would be network delay. And what we mean by network delay is buffering. Now, on a multiplexer, these devices are doing 64 kilobits per second in the transmission system. And remember what we discussed, what that actually is 8 bits representing the value of the sample, 8,000 times a second. And so a multiplexer, this is a device that takes a whole bunch of low-speed inputs and puts them onto a high-speed output. The worst case scenario is that you'd have to wait 1/8,000th of a second in order to get your stuff onto the high-speed output. So each multiplexer adds a delay, which is not very significant. But routers and Ethernet switches are going to add delay. Now, how does this actually happen? Well, think of an Ethernet switch. They're little boxes about this big, and they've got inputs and an output. And of course it works in both directions, but it's a lot easier to think of it just in one direction. Let's think we have 4 IP phones plugged into 4 ports on this Ethernet switch, and there's one outgoing circuit. Well, those 4 phones can't transmit all at the same time and have their stuff all actually sent at the same time because there's just one output. So they have to go in a round-robin fashion, one after another, sharing the single output out of this switch. And the way this works is that every input has a tiny little bit of memory associated with it called a buffer. And when we've got information coming in the inputs, it actually gets parked in this buffer, in this little bit of memory, and then the processor that's running the Ethernet switching function is going to service those buffers one after another, take a piece of information out of there and send them on the output. So what we end up with, in the worst case scenario on an Ethernet switch, you send something on your input, it gets parked in the buffer, but the processor's just finished serving your buffer, and so it goes through and sends information from all of the other inputs before it gets around to yours. And it can't send information faster than the rate that it goes out of the output. And so if you do some quick back of the envelope calculations, the worst case scenario for delay through an Ethernet switch is the length of time it takes to transmit a chunk of data. In an Ethernet switch, we're talking about a frame which is usually 1500 bytes. So how long it takes to transmit that on the output times the number of inputs. So if we decide to get clever and take all of the IP phones in our building and connect them together to a 256 port Ethernet switch, well then the worst case scenario for delay is you'd have to wait 256 times the length of time it takes to transmit a frame before your stuff would go through. And it depends what the speed of the output is, but you can do some more back of the envelope calculations and you can see that that's going to be significantly more than the 1/8,000th of a second that a multiplexer engenders. So Ethernet switches and routers introduce significant delays, and this would be one of the main components of a network delay. In traditional telephony, we don't have this problem because we're using multiplexers, which add 1/8 of a millisecond delay at each step. But when we're talking about voice over IP, we're not necessarily using multiplexers. We've added Ethernet switches and routers into the story, which add a lot of delay because if you want to think of it for long enough, you'll realize that the chunk of data that we're now transmitting is much bigger. And on both systems, you have to wait until every input transmits a chunk of data. In traditional telephony, that chunk of data is 1 byte. In voice over IP, that chunk of data is 1 LAN frame, which is 1500 bytes. And so the length of time you'd have to wait before every other input transmitted its 1500 bytes before you could send yours, you can start to think that that's a significantly longer delay. This would be what we call the network delay. And when we add the propagation delay, the network delay, and the delay engendered by the compression or coding function, then this would be the total end-to-end delay, and the design maximum is 150 milliseconds. Delay is one thing. Variability of delay is quite another, and we call variability of delay jitter. What's going on here is that at the transmitter we might be sending chunks of data in a nice regular timed manner with fixed intervals between each chunk of data, which is digitized speech of course, but at the receiver we don't receive these chunks of data which are digitized speech in a nice regular order. The time between each chunk starts varying. The mechanism that causes this is Ethernet switches and routers. Recall from our previous discussion the idea of an Ethernet switch where we've got 4 inputs and 1 output, and all 4 inputs try to transmit at the same time, so their information gets parked in a little buffer, and then the processor in the Ethernet switch then services those buffers one after another in a round robin. Now, if everybody was always transmitting all at the same time and the buffers were always full for all 4 of them, then any individual input would see a nice regular timing for the transmission of their data on the output. But the problem occurs when at one particular instant in time all of the buffers are full, and then a couple of milliseconds later 3 of the inputs stop transmitting and the 4th one still is. Well, then its buffer is just going to get serviced continuously, and then one of the other inputs starts saying so it has to start alternating between these 2, and then they're all full, so things slow down, and then there's just 1 again, and you can start to see that the delay caused by the Ethernet switch is going to be variable, and it's dependent on the traffic flow into it. And that's something that we cannot really control because we're talking about people speaking and or surfing the web and so forth through this communication network. So we're going to have jitter when we're doing voice over IP. We don't really have that problem in traditional telephony because all of the delays are fixed at 125 microseconds in traditional telephony. But as soon as we start doing voice over IP and we're using Ethernet switches and routers, then we're going to have variable delays caused by variable loading of these devices. The solution to this is to put a jitter buffer at the far